Okay, so now question number 8. We have shown that the relation R in the set A, which is equal to 1, 2, 3, 4, 5, given by R is equal to A comma B, such that the absolute value of A minus B is even, meaning that the difference between A and B, the absolute value of that is an even number. So you want to show that this relation is an equivalence relation. So let's first do this part, and then we have a couple more things here to do as well. So first of all, if basically a relation has to be an equivalence relation, you know that it has to be a reflexive relation, a transitive relation, and also a symmetric relation. So to show that R is reflexive, what you can do is that basically x comma x does belong to R for all x belonging to A, because basically x minus x is always 0, because x minus x, the absolute value of x minus x is equal to 0, which is even, right? So that is, and so you can say that then basically R is reflexive. R is reflexive. Moreover, you can say that to show that R is symmetric, let's assume that some x minus y, let's assume that some x comma y does belong to R. That basically implies that the absolute value of x minus y, is an even number, is even. And that basically does show that the absolute value of y minus x is also even, because basically the absolute value of x minus y is actually equal to the absolute value of y minus x for all x and y belonging to the set A, right? So which means that basically if the absolute value of y minus x is also even, that basically means that basically the order pair y comma x does belong to R. Since it does belong to R, that means that x comma y belongs to R, y comma x belongs to R. That means that basically R is symmetric. R is symmetric, right? And to show that R is transitive, you can assume that some x comma y, let some x comma y and y comma z belong to R. That implies that basically x minus y, that implies that the absolute value of x minus y basically is, and the absolute value of y minus z are even values, or even. So if the absolute value of x minus y and the absolute value of y minus x is equal to are even, what that means is that So there are probably two cases here at least. So if the so we need to consider basically the cases where the difference of two numbers is an even number. So first of all, you have the even integers, and you have the odd integers, right? So suppose that you have some odd integer. So you have the even integers, even and odd integers. So you can take even with even, meaning if I take this as 1 and take this as 2, what you can do is that you can take, for example, 1 with 1, you can take 1 with 2, you can take 2 with 1, which is the same thing, and 2 with 2. So 1 with 1 would be two even numbers, 1 with 2 would be an odd number and an even number, and 2 with 2 would be two odd numbers. And let's subtract two even numbers. For example, let's say you have 6 minus 4. These are two even numbers, and you'll get a 2. This is an even number. Let's subtract an odd number from an even number. So for example, you have 6 minus 3, which is equal to 3, which is an odd number. And let's subtract an odd number from an odd number. So for example, 5 minus 3, which is equal to 5 minus 3 is equal to 2, which is an even number. And you can basically produce more examples here. For example, 7 minus 5 is equal to 2 as well, which is again an even number. So that means that you either have basically two odd numbers or two even numbers, and if you subtract those numbers from one another, now we don't really care about the sign here, because here we have the absolute value functions, and the absolute value function takes care of the sign, and the sign is really not important right now anyway. So if you have an even number, so basically you have two cases here. So for example, related to this case, you have case number 1, which is basically x and y. X and y are both even, or are both even. Case number 2, you can say that x and y are both odd. And you can have the same argument for y and z, meaning that you can have case number 1 here for these two, meaning that you can say that y and z are both even, and case number 2, you can say that basically y and z are both odd. And then you need to consider each of these cases with each of the other two cases. Now suppose that, and here we want to show that basically x and z does belong to R as well, right? Meaning that the difference of x and z is again an even number, right? So now if I consider case 1, so I call this, for example, case 1, 1, and for the sake of simplicity, I call it case 1-1, and I call it case 2-1, and I call this case 1-2. I call it case basically 1-2, and I call this case 2, case 2-2, right? Or you can just enumerate them as 1, 2, 3, and 4. Let's not make it so complicated unnecessarily. So if I consider case 1 with 3, what I will get is that basically x and y are both even, and basically x and y are both even. I'm sorry, y and z are both even. We have no problem there, right? So if x and y are both even and y and z are both even, what that means is that well, y is an even number, y is an even number here, and x is an even number, z is an even number. So that means that x and z are both even, which implies that basically x minus, actually this is supposed to be z. So x and z are both even. So this implies that x minus z, the absolute value of that, doesn't really matter whether you use the absolute value function or not. But you can, if you want to be consistent with the problem, you can say that x minus z is an even number. And what that means is that x comma z belongs to R, right? Now if I consider case 1 with 4, what I'm saying here is that x and y are both even, and x and y and z are both odd, which is not possible. Because here y is odd, here y is even. Y cannot be both odd and even at the same time. So we cannot consider this case. Now if I consider case 2 with 3, basically 2 and 3 here, so here I'm saying that x and y are both odd, and here I'm saying that x and y are both odd, and here I'm saying that y and z are both even, which is not possible. Because here y is odd and here y is even, and so of course y cannot be simultaneously odd and even, so we cannot consider this case. If I consider 2 with 4, what I have here is that basically x and y are both odd, and y and z are both odd, which there is no problem with that. And what that means is that then x and z are both odd. Which implies that x minus z, or you can say the absolute value of that, is an even number. As we discussed here. We saw that when we had two odd numbers subtracted from one another, we got an even number, right? So if x minus z is an even number, then you can say that x comma z does belong to R, right? So in each of these cases, basically here the case was simply impossible. Here the case was simply impossible, and in these two cases where the cases were actually possible, we got x comma z belongs to R. So that means that basically x comma y and y comma z belonging to R, which means that x comma y and y comma z belonging to R implies that x comma z does belong to R, which means that basically R is transitive. R is transitive. And so what we have shown is that basically R is reflexive. R is reflexive, symmetric and transitive. And therefore R is an equivalence relation. R is an equivalence relation. Now, when you have an equivalence relation, you will of course get everything that comes with an equivalence relation, meaning that all of those equivalence classes and partitions and subdivisions in the set that you are basically considering, meaning that in this set over here you will have some subdivisions relative to that equivalence relation, and so those subdivisions of the set A would be this set here, and basically and this set here. And we argued that basically the two sets, in these two sets, every element will be relative to, of course, under R, every element is related to one another. In this set again, since this is another basically equivalence class, every element over here is related to one another. And of course, no element of this set is related to any of the elements of this set. And that's what we want to show in the next part of this example. So let me go and get some space here, and then we will show that as well. Okay, so now basically what we had here was a set, and basically the set was basically A, which was equal to 1, 2, 3, 4, 5, and 4 and 5, and basically we had two partitions or subdivisions of the same set, which you can call basically these two sets, which are basically 1, 3, and 5, 1, 3, and 5, and 2, 4, right? So you can see that this is basically all of this is a subset of the set A, which contains only even numbers, and this is a subset of the set A, which contains only odd numbers. And we want to show that basically, let's call this set, for example, B, and let's call this set C. We want to show that all the elements of B and C, all the elements of B, let's say, are related to one another, let's say to each other. All the elements of B are related to each other. Moreover, we want to show that number 1, number 2, all the elements of C are related to each other, and number 3, basically no elements of B is related to C, and vice versa. we want to show that under R, basically that is the case. Right? So that is what we want to show. Now, in order to do that, basically you know that basically about the part 1, all the elements of B are related to each other, right? So you know that basically the relation R that we had was basically all the ordered pairs x comma y, such that the absolute value of x minus y is even, right? Now you can say that x comma y belongs to R for every x and y belonging to B, and the reason for that is that because B contains all odd elements, and we showed that basically whenever you subtract any odd element from another, any odd number from another odd number, the result is going to be even. So that means that all the ordered pairs that you can create out of the elements of the set B is going to be in R, meaning that the Cartesian product of B and B is actually going to be a subset of R, right? It's actually going to be a subset of R. Or you can say that to express this more basically in a better way, I can say that all the elements of the Cartesian product of B and B exist or lie in R. That I can say, right? Now number two, I want to show that all the elements of C are also related under R. So number 2, I can say that based on this R, I can say that x and y belongs to R for all the elements of x and y belonging to C. And the reason for that is that basically C contains only even numbers. And of course we showed before that when you subtract an even number from any other even number, the result is going to be an even number, which satisfies this rule, which means that basically all the elements of the Cartesian product of C and C belong to R, right? So that is that. And of course, part 3 of this question, you can say that there exists there exists no element, no x and y, no element x and y belonging to R, such that basically either x belongs to, for example, B and y belongs to C, or x belongs to C, for example, and y belongs to B, meaning that either you take your x from B and you take your y from C, or you take your x from C and you take your y from B. Either of these two cases, there exists no x and no ordered pair of x and y that belongs to R. Or you can say the same statement in this way. You can say that x comma y does not belong to R if any of these two is the case. If either x belongs to B and y belongs to C, or basically x belongs to C and y belongs to B. And the reason for that is that basically B contains odd numbers. B contains only odd numbers, and C contains only even numbers. And the difference of any odd and even numbers cannot be an even number. Which means that no elements of B is related to C under R and vice versa. Meaning that no element of C is related to any of the elements of B under R, right? So that is question number 8. So here basically we basically have the idea of a, so this is some set under study, and this is some relation that we have. The relation is basically this, and we have basically, based on this relation, the set that we have is basically broken down into two partitions or into two subdivisions, and we express this idea exactly as the following. We said that given an arbitrary equivalence relation R, and of course the relation has to be an equivalence relation, meaning that the relation has to be reflexive, it has to be symmetric, and it has to be transitive as well. So then you can say that given an equivalence relation R, relation R in an arbitrary set X. R divides X into mutually disjoint subsets, subsets A of I called partitions or subdivisions, of X satisfying number one, all elements of A of I are related to each other. All elements of A of I are related to each other, which is basically what we saw in the case of, for example, all of the elements of B, for example, or all of the elements of C. They were all related to each other. So all elements of A of I are related to each other for all I. And number two, we said that no element of A of J, is related to any element of A of J. I'm sorry, this is supposed to be A of I, of course. So no element of A of I is related to any element of A of J, A of J, basically if I is not equal to J. And number three, you can say that the union of A of J is equal to X, and A of I intersection with A of J is equal to the null set for A not equal to J. So basically we said that all elements of A of I are related to each other for all I. What that means is that over here we saw that basically all the elements of this set are related to each other, and by the same logic we saw that all the elements of this set are related to each other. Moreover, we said that no element of A of I are related to any element of A of J when I is not equal to J. Meaning that we saw that basically no element of B was related to any of the elements of C and vice versa, right? And moreover, here we said that the union of A of J is equal to X, meaning that in this case you can see that B union C is of course equal to A. And also B intersection C is equal to the null set, because they have nothing in common. And that's basically what we see here. Union of A of J is equal to X. That's a notation that you use when you mean to say that, for example, you have A1 union with A2, union with A3, union with all the way up to, for example, A of n. When you want to write when you want to write in a more compact way, you write it as union of A of j, for example, as j goes from 1 to n, for example. That's the exact same thing. So when you say union of A of j is equal to x, that means that all the subsets or all of the partitions of x, when you put all of them together and when you take the union of all of those sets, that's equal to x. And the intersection of A of I and A of j when I is not equal to j is equal to the non-set, which is basically what we saw over here, which is basically another way of saying that the sets are mutually disjoint. Mutually disjoint set, meaning that they have nothing in common, right? So that was basically question number 8, right? So in the next video we will talk about question number 9. See you in the next video.